A lot of the things that I would like to talk about today is about all the prediction models that we put out there in the world, and the fact that we want to trust these models when Google Maps tells us that it's going to take us 30 minutes to go to the airport. We don't want it to take an hour because we're going to miss our flight. And so I've been thinking a lot about the work that we can put in terms of making sure that the predictions that we put out there are accurate and can be trusted. And so, I just took the example of traffic here, but you can think about examples that are like potentially even more harmful. And so I'm really excited to spend the next 45 minutes or the next hour with you talking about this topic about prediction quality, because this is something that I am incredibly passionate about. And I really want us to think about this prime together, and one of the things I'd love to achieve today is for you to keep on thinking about these questions that are really complex and that may not be front of mind for everyone. So yeah, what do I mean by developing robust and trustworthy model? I mean putting something online where we want to trust the predictions, whether it is something for a 30-year-old male in the United States or whether it's a prediction about a 70-year-old female in India, for example. We want to be confident in metrics that we put out there when we say that a model has 0.8 recall for 0.95 precision. We want to make sure that this is something that's actually holding true. And I really liked the point from the previous talk about we want this to be true in the lab, in a clinical setting, is I think the word that you use. But most importantly, we want this to be true once our model is in the wild, being used by real people. And so this is something that I will be excited to touch upon. And then we also want models that are robust to adversarial attacks and things like that. As Don mentioned, I'm on the Central Applied Science team, and we're really a team that ties the areas of academic research and puts them in practice in a scientifically rigorous way. In the industry, and really with the goal to have both better and safer use of AI and machine learning in the industry. So this is all maybe a little bit abstract. I just want to think about maybe a concrete problem. So I work at Meta, and one of the things that has been a top priority for us is to ensure that we provide age-appropriate experiences online. We don't want a random adult to be able to message a teenager. We don't want minors to see alcohol ads or to have access to dating apps. And so what do we do for that? Obviously, users provide their birth date when they sign up. So you can say, well, if they say they're over 18, then maybe they're over 18. Unfortunately, users are not always accurate or sometimes honest about their age. And so on top of this user-provided information, if we really want to be leaders in the space of youth protection, we need to have accurate age predictions to make sure that we protect minors online. And so the reason I put this photo here is that I want to ask you, how do we make the difference between a 17 and an 18-year-old? And maybe this image is someone a little bit younger, but there's a lot of times when like I challenge you to go in the street and see a group of young people and ask yourself, are they minors? Are they adults? It can be really challenging to differentiate. And so that's where we really want to think about how do we like make the difference and trust that we are able to make that difference. And so we want to be able to build the best models. We want our models to perform to the standards that we need and evaluate the risks of having mistakes in our models. And we want our models perform all over the world on the entire population, whether it's people in the United States, people in Iceland, or people in other parts of the world. And if we keep the example of age, like taking into account the differences in culture that make people of a certain age look very different across the world. So just going back here, I wanted to just take a step back and think about like our the role that a central team has in this space in terms of really pushing innovation forward across the company and making sure that these scientific methodologies make their way to the different product teams. So when I think about these robust and trustworthy models, I like to break this idea into different blocks that really build on top of each other. Eventually, what we care about is the top, is having like high quality, trustworthy predictions. But if we want to be accurate there and actually have full trust in these models, we need to think about what is needed to get there. And today, I really want us to think from the ground up about the main foundations that are going to enable us to build this trustworthy model. So I'll first go through trying to convince you about, if you're not already convinced, I hope some of you are already convinced, that will make things easier, about the importance of ground truth. And I'll go into more details in terms of like what I mean by ground truth, but really like as something that's a foundation for all modeling work. I really want you to leave today convinced about the importance that it has for training models, but in my mind, even more importantly, for evaluating their performance. And that's really, to me, where I see this trust is in this evaluation methodology. And then once we have our strong basis, we can think about being inventive in terms of noveling techniques. And there's a lot of things that we can do to leverage patterns of interactions and graphs, even at a place like Meta, where you can imagine the size of graphs being like billions of nodes and that other level of number of edges. And so we have to be very like pushing innovation in terms of like how we build these graph models at scale. But I think there's a lot of really exciting work going on in that space as well. But so let's get started with the foundations. And as I said, to me, like the foundation for this like trustworthy model is the ground truth data that we use for this model. So first, let's agree on what I call ground truth, because I think that's something that may be a word that's used differently by different people. So for me, ground truth is the data set that contains the values that we want to infer for a particular population of interest. So these may be annotated data sets like we were talking about earlier. This may be labels that are provided by crowdsourcing or by human labels that go and provide information. This may be information that comes from survey, or this may be self-provided information from users, like we were talking about users providing their age. One of the challenge with this ground truth, and that's the reason why I wanted to make sure we were all using the same definition, is that they may still, even if we call it ground truth, there may still be mistakes and issues with this data set. If we survey people may not understand the question properly or not respond trustfully. If we ask human labels to label, they may make mistakes. They may be missing information to provide accurate decisions. So there's a lot of things that can be wrong with this data set. Another potential challenge, for example, if we do surveys, is that if we survey people in San Francisco, we're not going to have a representative sample of all the people using social media, and so there's a lot of different challenges that we can have, and so once we have these ground truth data sets, obviously we can use it for training models, although you may argue that a lot of models may not necessarily require ground truth using like transfer learning or some other techniques. But one place where I believe we will continue to use and need ground truth is for model evaluation. For me, this is really the measuring stick that enable us to understand how well models are performing. In some sense, like, I tend to feel like what you feed the model in training, I mean, if you have high quality data, your model is likely going to be better, but your model may be robust to having some noise. When we think about the evaluation, if we really want to trust that our 80% recall is actually 80%, we need to trust the data that this number is based on. And so that's really something that really puts the emphasis on the quality of these evaluation data sets. If we do evaluation on 10 data points, then we're going to have error bars that are so large that maybe the recall is 80%, but with like such large confidence that if we improve the model, we're not actually going to be able to see any statistically significant changes. Or if we have errors in our evaluation data sets, our precision or recall numbers are also not going to be corresponding to how the model actually perform. So by now, I hope I've kind of touched upon the reason why I've been really interested in studying how we get high quality ground truth data sets. And so have worked with from seeing how people have worked with ground truth, we've decided to create a framework to help teams think through the quality of their ground truth data sets. Obviously, this is not a space that is brand new. I think there's a lot of body of work that exists in this space. But one thing that we've realized is that we haven't really had like a consistent way for people to think about what it means to have a high-quality ground truth data set. And even internally, we feel like all speaking the same language, all having the same tools to work through things is something that has been really, really positive. And so we've created this framework that we call the Ground Truth Maturity Framework, which is based on the scientific literature and the statistics literature, but really built for practitioners to help them in their development and in their evaluation of predictive models. The goal of this framework is threefold. I think first we want to educate and provide guidance so that people actually realize the importance of having a trustworthy evaluation data set. And to me, it's a lot about breaking the we don't know what we don't know, and that's also a theme that was there on the previous data set. If we only have like a lot of people who work in the machine learning space may not know what things to look for in an evaluation data set. Second, we want to provide quantitative metrics so that practitioners understand the risks and decide on potentially necessary improvements that they want to provide to that evaluation data set. And third, it may be a good idea to not only point out at things that can be improved, but also provide people with tools to actually make these improvements. And so the way you can think about this is you going to the car mechanic and you likely don't know what all potential things can go wrong in your car. And you don't want to know about this. You trust that some people over the years have figured out all the different checks and all the different things that need to be looked at over your car, and they really have these different dimensions that they're going to look at one after the others. And then if they say that a dimension is requiring improvement, so for example, your car has old tires, you want to understand like the cost, you want to understand how much it's gonna, how much time it's gonna take you to change this tire, but you also want to understand what are the risks of not changing these tires. And so through this analogy, I just like want you to think about how we've been thinking about developing the ground truth maturity framework as this way to provide clear guidance for practitioners who don't have to all have a PhD in statistics to understand the research, to understand all the relevant information, and can really make informed decisions in terms of the risks associated with investing or not investing in a certain space, in terms of how much time will it take their engineers or their data engineers to make their changes, and in a way that's very easily communicable, whatever, and something that we can like track over time and see improvements. So what is this ground truth maturity framework in practice? We've broken down like the same way as for the car, we may be checking several things. Here we are checking seven different steps. Well, initially we want to understand like what is it that we are measuring. For example, if we're predicting people's age, this is a pretty simple thing to define. If we are predicting the topic of a post, what is the space in which we're predicting, and so on. But then eventually we really want to think about like how ground truth is defined and what is the model actually predicting, and whether in the collection of this data set there has been some like important errors that have happened. Maybe a system was down, or there was like logging issues, like these kinds of big flaws that should be easy to fix. And then we want to think about whether the data set is representative. So it means, does it represent the population that we are trying to predict for? So if we're aiming to predict for an entire population, and our data set only has males of 30 years old, we may have a gap between what our sample is like and what our target population is like. Then we want our data set to be accurate, meaning that we don't have too many errors. If we have the account of a 30-year-old, we should not say that they're 50-year-old, and so on. And we also want our data set to be reliable, which means that if multiple people looked at the same examples, they would provide the same label. And then we also want to make sure that we have enough data, that the data is collected in a timely manner, that especially for things that may change over time. And we also want to be efficient, like the amount of time and money that we spend at collecting this data set is something that we also want to think about. And so now that we have these 7 dimensions, we can really think about guiding people much more specifically in terms of how they can improve. So for each of these dimensions, we tie a level of maturity that describes how well this specific dimension is measured and whether improvements are needed. So it goes from unmeasured, which is basically like, we have not been thinking about this. This is the first time I hear about it. This is a new concept, which, to be honest, is something that is not infrequent for people to realize that, oh, representativity matter. I can't just take any data set and call it good enough. And all the way to, okay, we have looked into this dimension, we know how well we're doing, but we need to improve. And then eventually potentially deciding that this is actually good enough and not much more work is needed. So what this ground truth maturity framework provides is this report card, which provides for each of the different steps a level of maturity. And the idea is not that everything needs to be green. The idea is really to think about how we prioritize improvements, what the risks of different steps being yellow or red are, and whether it's actually needed to go into the green. Depending on how a model is used, it may be fine to have dimensions that are at low maturity, and these are risks that are fine taking because they're fairly minimal. If we use a model for protecting minors, maybe a lot of things will be more in the green than for like a ranking model that's going to like change which friends you see first in your feed. So this is something that like we work with teams on in terms of understanding their priorities, and then this is something that's also very like easy to communicate, to track and communicate progress and make specific goals in terms of improvements. So eventually, like the way this process looks like is that we have these initial assessments. We agree on the results and decide for each dimensions whether we want to make improvements or whether we're fine with the current status. If improvements are needed, then we have a set of tools, and I'll provide some examples in a little bit in terms of like, okay, how do we actually get to the next level or to the level that we deem required for the quality of this data set. And then we're gonna, once we make this improvement, we're gonna update and then go back to the assessment, decide if we want to continue improving and so on. Obviously, once we're in the green, we're not done yet. We still want to keep track of how things are going, both because the requirements and the risks may change, but also because the quality of the data set may change over time. For example, one of the dimensions was the timeliness of the data set. If we get our data sets go old without having any new data come in, then maybe this dimension that was fine at the time of the initial assessment may no longer be in the future. So now I'm not going to go into all the different steps because we would still be here by dinner time. But I still feel like it will be useful to go into one of the dimensions. And so let's just pick the representativity. I feel like there's a lot of things that I find useful to discuss. It's also something that comes a lot in terms of questions of fairness and responsibility of ML models. So a theme that comes dear to me. So why do we care about representativity? Why is it important when we think about responsible AI and fairness? First, because, I mean, if we train the model on many more female than male, then maybe our model will perform better on female somehow. Sometimes it's the contrary. But more importantly, if our evaluation has many more females than male, then we're going to weigh the performance of the model on female much more heavily than we do it on males. And obviously, this is all the more important that the dimension that we're trying to predict varies based on, in this case, gender. Because if gender is a variable that is not predictive in the model, then it's not an issue. But if, for example, the female population tends to be older than the male population, then we want to fix this. And so to measure the difference between our sample population, which is where we have our ground truth, and the target population, which is all the users of a social media platform, we look at the absolute standardized mean deviation. And this is a metric that quantifies the value of the variable we're trying to predict for our sample population and for our target population. And so that really gives a quantitative metric for teams to track over time and see how far off these distributions are. So if these distributions are actually fairly distinct, what can we do? And so one of the tools that we have developed at Meta, and it was actually recently open sourced, is called Balance. And what we can do to improve representativity is to use weights that are going to weigh, in our case, the male population differently from the female population, so that when we start, our sample population is distinct from the real world population, but using weights, we bring things more in balance. And so this is something that we have been using. And I took the example of just having gender being one variable, but obviously what we typically want to do is think about a lot of different dimensions, and we're actually starting to think about not just like these variables that are like explicit, but how we can do it using like embeddings and things like that for more complex analysis. And so what this does eventually is that it adjusts these biases that we have in the data set. I started with the case of having like imbalanced population, but you can even think about cases where we have a full blind spot for some segments of the population. To go back to the example of age, we want to model the age of people, not just in the United States, not just in countries that have like a language that is widespread, where it is easy to get like surveys and human labelers to provide information about the accounts. We also want to be able to know how well our models are performing in countries like Iceland or like other countries where we are not able to get enough data to really understand the performance of our model. So here the risk is not necessarily about biases, but it's really about not knowing how well we're performing on certain segments. And so for this, well, first I would encourage you to check out the paper, which is going to be presented at the end of today. But just to give you a sense of it, if we think about missing some segments of the population, we can still think about how similar these segments are to segments for which we have data, and then interpolate from there. Obviously, there's a lot more complexities behind this, and so I encourage you to go learn more. But this is another approach that we have developed to enable us to trust models, or to decide that we don't trust them. That's definitely another outcome, to decide that the models are not performing well enough in portions of populations where we do not have data. So let's look at some concrete examples. We have worked with teams across Meta on quite a few examples, but this is one where I feel like it touches upon some of the different dimensions. So we want to think about like topic classification. So for example, for creators on Instagram, we want to know whether they post about sports or whether they want to post about music and so on. And so we've worked with the team to have them apply the ground truth majority framework, look at the assessment across the 7 dimensions, and based on the assessment, they were able to prioritize certain investments. 2 big areas that were follow-ups from there. First one was the reliability. So there was human labelers who were looking at the accounts and deciding like what topics people were posting about, and we were noticing a lot of differences across raters, and so the reliability dimension noticed this, and so this is something that using another tool that we have developed called CLARA, which stands for Confidence of Labels and Raters, we were able to identify which labelers were performing not as well on certain tasks, and then provided guidance and training for this to improve, and so over 20% improvement in the performance of these labelers. One other outcome of this, which is partly one of the motivations also for me being here, was for them to really understand the importance of their evaluation data sets and the importance of having data sets that were not noisy, so that they would be able to measure improvements of their model. When we started working with them, because there were so many errors in the evaluation data set, the improvements in the training and in the modeling were not detected by the metrics, because there was so much noise and so many errors in the evaluation data sets. And so the main thing that we were able to for them to understand is that the evaluation was really their measuring stick, and they had to trust that measuring stick, and then they could do the improvements on the training. Otherwise, they could change a lot of things in the training and not being able to detect it downstream. So this is one of the concrete examples that we've had, and then have applied this with teams across the company. Beyond the ground truth maturity framework, we have a lot of work around developing best practices, and this goes in the field of experimentation, in the field of goal setting. I encourage you to look at this note that we published a few months ago, with the idea to, again, like, all speak the same language, not reinvent the wheel, and have people be more efficient in terms of how they use data in a reasonable way. So now that we have strong foundation, or at least we know how to get strong foundation, we can build on top of this. We have our measuring stick. We trust our measuring stick. We can develop fancy models and really think about new techniques that we can develop to get the best inferences and decision. And so I was mentioning earlier that one of the areas where I have been really interested in pushing innovation forward is in the field of graph learning and network science. And being at KDD, I know a lot of you work in this space. One of the things that I've been really interested in is making this kind of a default tool for people to use, even at scales of graphs with billions of nodes and hundreds of billions of edges, and so to us, that's where a lot of the innovation comes in, is how do we develop these algorithms that may not be the most complex, but that are able to scale at a really large, for really large sizes. So, as you can imagine, being a social network at Meta, we have a lot of graphs and interactions. So much that it can actually be a little bit overwhelming. Like, how do you represent all of these interactions? And so that's one of the things that we have been working on. So if we think about like a conversation, so you have a post and you have people responding to that post or having reactions to that post, and then people responding to these comments and responding to these responses. It forms something quite complex. So if we take the example of this conversation here, we have one first person who creates a comment, a second person who replies, the first person who's going to reply to that first person, they're also going to love the response of that person. Another person is going to be angry with that response, and then other people are going to comment or like. But so what we've done here is that we've turned this conversation with a lot of things happening into a graph, which already is something that we feel like is much easier for us to process as researchers. Then the graph is still really big, and so we want to break it down a little bit further into these patterns of interactions that may repeat over time. For example, we have this first person who creates a comment, a second person who replies, a third person who's angry at the reply. We also have that first person who commented, a second person who replies, but then the first person sends another reply, and so on. And so from these little bits of conversation, we've created a series of motifs of interactions that we can then use as features to downstream model to like use these patterns for making better predictions. One example that I've been really excited about is our work on conflict detection. Unfortunately, public groups are a place that can be toxic and can lead to interpersonal conflict, leading because of turnover of membership, because sometimes like people have like anonymity associated with it, also because of differences in goals and opinions, and so we want these conversations to be productive and respectful and identify when things become toxic, and so we used these patterns. As you can imagine, like the patterns that come up from toxic interactions are things that have a certain pattern to them, and so we have been able to leverage these motifs to detect conflict, but also to kind of take a step back and understand and like have interpretable results that help us identify what kind of triggers this conflict and what can be bringing productive and constructive discussions versus things that are just toxic and not useful. So this is something where really having these motifs that are interpretable can both provide like the complexity of interactions, but also help us understand what is actually going on. Another area where we have used this is for comment ranking, and that has enabled us for people to actually see the comments that they care about the most being ranked higher in a post or on an ad, and this is something where people have actually expressed the value in having better comments, especially on posts that have a lot of interactions. If you have hundreds and hundreds of comments, you don't necessarily want to go through the list of all of them. So now I have this slide to make sure that I have still a little bit of your attention after 40 minutes, which really the main thing that I want us to think about is how content may not always be sufficient for making accurate predictions, and so we have this example here where we have a photo of marijuana and a photo of tempura broccoli. On Facebook, it is illegal to sell regulated goods. Unfortunately, people do it anyway. And what is challenging for us is that based on this content, it can be really hard to make the difference both for a human as well as for a computer. That's actually a case where a computer likely does much better than we are. So how do we go beyond the content that we have? We had the example of the interaction motifs earlier, and this is definitely something that we can use here. The way people are going to react and interact with a photo of broccoli is going to be very different from the way people are going to react from a photo of marijuana. But we also thought about how much, what else we can do, because we can look at the patterns of interactions, but we can also think about who is interacting and how a certain person is interacting. If I interact with a post, if I like a post, it's likely going to mean something different than if my dad interacts with a post, or if my lifelong enemy interacts with the post. I don't know who that person is, but imagine they exist. And so there's a lot of information about who and how people are interacting that can be integrated when we make these predictions. And so we have information about this person. We have information about giving a like has a very different signal than giving an anger reaction. So from these patterns of interactions, we want to decide, is an account abusive or is an account hate speech? And here we really want to think about all the information that we can embed in a way that may be good for people who are trying to go over algorithms. The least people can game the system, the better for all these abusive detection. So we went one step further from the motif work and really embedded information about accounts, embedded information about the interaction, and feed this into a sequence encoder that really looks at the sequence of interactions on a post or the sequence of interaction of an account, and then is being trained to make better predictions. So for today, I had two main goals. The primary one was to share the state of the art that we have developed in terms of best practices for thinking about model evaluation as something that is really central to building the trust and the quality of models and decisions. And then once we have this strong foundation, we can continue developing new modeling techniques, and I've given you a couple of examples of work that we've done related to network science and graph learning that have enabled us to improve some classification and ranking tasks across numerous applications at Meta, in particular in fighting abuse or having constructive conversations online. This is the work of a very large number of people. I think I've represented them all, but a lot of amazing researchers that are making this work possible. And so couldn't thank them enough. On that note, I will just leave you with some notes about the kind of work that we do. I think I try to talk about the role that we have in terms of really pushing science in the industry with practitioners, and this is something that I think as researchers we have a big role to play in terms of pushing innovation and making it available, because if it just stays in the lab, there's a lot to be lost. So with that, thank you.